concept we proposed a few years ago, and we developed efficient numerical method to construct solution landscapes for different complex systems. So today I'm going to deliver 3 messages. First one is what is the solution landscape? The second is how to compute solution landscape. And the last one is what we can do with solution landscape. Okay, let's start. In the world of classical mechanics, people was once believed that as long as we know the initial state of a particle, then we can predict the trajectory of this particle. So just like we solve a linear equation, the exact solution is known. So we know its trajectory in the future time. However, after studying the 3-body problem, people found that the answer is wrong, because this 3-body problem is essential the complex nonlinear system. So if there is some perturbation at the initial state, we cannot predict its trajectory. So this is the simplest complex system for the 3-body problem. And actually, in nature, our world is composed of various complex systems, like the gene regularity network. So this is a typical nonlinear complex system. So the genes interact with each other, then they can perform different functions and decide different cell fates. And in the middle one is another typical complex system. Example of complex systems is so-called spin glass. It's a disordered system, and it looks like random. But this random feature is actually the metastable state. And this Georgia Palissy found this hidden patterns in this disordered complex system and won the Nobel Prize in 2021. So what do we care about this complex system? One characteristic of complex systems is multi-stability, also called multiple equilibrium. Okay, so this is the simplest complex system. It's so-called a bistable system. Here you can see that we have 2 stable states, 1 and 3, and in the middle one is a transition state. So this state 2 connect two different metastable stable state. Okay. And this in the protein folding from the unfolded state to the native state, they need to fold many times in order to achieve the energy minima, the global energy minimizer. So it has to overcome many energy barriers in order to fold. Okay. This multi-stability describes the equilibrium property of the complex system, and fluctuation describes the nonlinear, non-equilibrium properties of the complex systems. So we know this fluctuation exists in the natural world. So by using this fluctuation, what we can determine whether a system has a single equilibrium state or it has we have multiple equilibrium states. Again, for this bistable system, if we have the fluctuation, then usually they can stay around in a local minimizer, but they have some small probability they can jump over to another local minimum. And after a long time, if you see the distribution of this particle, you can see those bimodal distribution. So it implies it has two steady state. So due to this noise-driven transition, so we know this famous phase transition in physics. So the transition from one equilibrium state to another equilibrium state. For example, this nucleation event, this bubble formation, rain droplet formation, something like that. And also the quantum tunneling and the activation event, they all belong to this phase transition. So if we want consider both equilibrium properties and the non-equilibrium phase transition in a unified mathematical framework, we usually can use this energy landscape to describe it. So this energy landscape is nothing but a mapping of all possible configuration of the system to their energies. And here, there's an example of this energy landscape, and you'll see many local minimizers corresponding to the metastable state or the stable state of this system. And this particle can jump from one metastable state to another metastable state. This corresponding to the phase transition. And many practical problems in physics, chemistry, life science, they can be reduced to solving the minimization problems in this energy landscape. Okay, trying to find those minimizers of this energy landscape. Here is some examples of the energy landscape. For example, this in the quantum physics, we see the nuclear shifts. Okay, and in the chemical reactions from reactant to a product, it has to overcome an energy barrier. Again, there's another picture for the protein folding. And in life science, we consider the cell cycle. You can visualize using the energy landscape. So if we want to study the energy landscape, what's the most important information we want to achieve? Actually, here we are looking for the stationary point, also called a fixed point, critical point. Okay, the stationary point is just the point its energy derivative is equal to 0. Okay, so this first derivative is equal to 0. Okay, but if we want to check its stability, okay, first derivative is not enough. We have to calculate its second derivative. Okay, it's Hessian matrix. If its Hessian is positive definite, it means it's all curvature is a positive curvature. It means it is a local minimum. And if Hessian has both positive and negative eigenvalues, it means it is a saddle point. And this is a typical example of a saddle point. So along this direction, okay, this direction, it is a local minimum. It's stable. But along the other direction, it is a local maximum. So it is an unstable direction. Okay. So in mathematics, we can borrow the famous Morse theory to describe the properties of critical points. Okay. So this Master Morse, American mathematician, developed the variation theory in lots of with applications to equivalent properties in mathematical physics, so-called Morse theory. And it introduced a Morse index of a non-degenerate saddle point. This non-degenerate means its the eigenvalue of its Hessian matrix is non-zero. Okay, so it's no flat directions. Okay, either positive or negative. And its Morse index is the maximum dimension of a subspace which its Hessian is negative definite. In other words, it means the number of negative eigenvalues of its Hessian matrix. Using this definition, we can define an index k saddle point. It is a maximum on a k-dimensional space, okay, and it's a local minimum on its orthogonal subspace. Okay. And here we can use this definition classify all stationary points. Okay. If k is equal to 0, it means it's a local minimum. And if k is equal to 1, it's index 1 saddle, and k is equal to 2 is 2 saddle, so on. Okay. And in physics, people are interested in this index 1 saddle point. It's also called transition state. Okay, because this transition state has the highest energy along the minimum energy path. Okay, so here you can see that those two blue point is a local minimum, and this red point is the transition state. Okay, it has only one unstable direction, and along this unstable direction, it actually connects those two local minimums, follow the gradient flow. Okay, so as long as you know this transition state, you can find connected two local minimums. Okay, that's why this transition state is important. Okay, so in practice, how to find those multiple solutions. Okay, so we know many methods have been developed to compute a local minimum. Okay, try to find stable solutions. For example, like the gradient descent dynamics. Okay, you either fx is an energy function or energy functional. Okay, you can just use the gradient flow. Okay, give a good initial gas. You follow this gradient flow, it will convert to a stable solution. Okay, or you can formulate your problem to an optimization problem. Okay, then you can apply efficient optimization method to obtain the solution which corresponding to the stable solution. Okay. And also there are many existing methods to find these multiple solutions of the nonlinear partial differential equations, okay, like the minimax method, deflation techniques, also the homotopy method, okay, to try to find this multiple solutions. And another approach is often used for this real event. It's mainly focusing on the index one saddle point. Okay. One type is the path finding method to compute the minimum energy path connecting two local minimums. For example, the string method developed by Professor Wei Nanyi, Wei Qingzhen, and Ike van der Eyden. Okay. Here you see they have initial string and then relax it by the gradient flow, and it will converge to this minimum energy path connecting those local minimums. And the point with the highest energy corresponding to the index one saddle point. Okay, and if you want to have the accurate transition state, you need to make more discretized point. Okay. The other one is the surface walking method. Okay. Surface walking method, it locate the index one saddle point. Okay. So instead of using the gradient flow, it will convert to a local minimum. This surface walking method can find this transition index one saddle point. Okay, like the diamond method, Jenkins standard dynamics, so on. Okay. Okay. Now the question is, although we have many existing methods to find those multiple solutions, okay, still how to find the global minimum and the relations between different minima on the energy landscape is still a long-standing problem in computational mathematics or computational physics. Okay, as I mentioned, usually we take a good initial guess, we follow the gradient flow, hopefully we find a solution. If there exists other local minimum, we need to tune initial guess. Okay, try to find another good initial guess and find another solution. Okay, and another approach for the real event. First, we find a local minimum. Then we try to find connected a new index one saddles. Okay, because this one saddle connecting two local minimums, so it relaxes it. It hopefully find another local minimum. Okay, so you just do the local search on the energy landscape. Hopefully, you can find more index one saddles and more local minimums. Okay, but the challenge is how to efficiently construct the global energy landscape without fine-tuning the initial guess and avoid those extensive computing. Okay, that's a big challenge. To solve this problem, we proposed a new concept, so-called solution landscape. Okay. This is the definition we give. Okay, this solution landscape is a pathway map consisting of all stationary points and their connections. These stationary points include both stable minimizer on the bottom ones and unstable saddle points. Okay. And this pathway map means different local minimum connected by index one saddle points, and one saddle connected by two saddles, and a low index saddle always connected by high index saddles. Okay. This we call the solution landscape. Okay. we can use this family tree or this genealogy to understand the solution landscape. Okay, so here, if I think in this audience, okay, we have the students, right? The students is the local minimum. Okay, and for us, the junior faculty, okay, we have children, so we are the index one saddles. Okay, if the senior faculty, like Professor Jung, maybe you are the index two saddle point. So you have the grandson and okay. So here, everyone has a unique family tree. Okay, it's just like every PDE province. Okay, its solution landscape also uniquely determined. Okay, and and this solution actually has some relationships. Okay, like if we have more than one children, okay, their relations, their connections connected by fathers and mother, but the relation with their cousins has to connected with grandfather and grandmother. Okay, so this is just a description of the solution landscape. And here, the mathematical foundation of the solution landscape again still based on the Morse theory. Okay, here we define this Morse function. Okay, so and this Morse function is a smooth function on closed d-dimension space. Okay, manifold, and all critical points of Morse function are non-degenerate. And on this Morse function, we can define this flow map. Okay, this flow lines is nothing but this gradient flow. Okay, so we use this 2D example. Okay, here you see that this point A is a local maximum because it's a two-dimensional space, so it's an index 2 saddle point. Okay, this from A there are many flow lines. Okay, though most flow lines will converge to EFG's 3 local minimums. But there are some special flow lines. It's the blue, this black lines. Okay, they connect those B, C, D index 1 saddle points. Okay, and starting from B, the flow lines will converge to E and F. C connect E and G, and D connect F and G, so that we can map the this solution, the energy landscape to the solution landscape. And you know this energy landscape can only visualize 2D or 3D. Okay, if it's high dimensional space, you cannot visualize it. But for any dimension, we can use the solution landscape to quantify those solutions. Okay. Okay, and here if we use the Morse-Smith-Witten complex, okay, we can guarantee that the flow lines, okay, always collecting from high index saddle point to the low index saddle point, which means B cannot connect C. Okay, B has to connect local minimum E and F. Okay. And more importantly, all minima are connected by this index 1 saddles as a connected graph, which means none of this local minimum is isolated. Okay, as long as you find all possible index 1 saddles, you can find all local minimum, including the global one. Okay, okay, so that's the definition of the solution landscape and its theoretical foundation. Okay, and practically how to construct this solution landscape. Okay, and here the key challenge is how to efficiently compute any index saddle points in the solution landscape. Because we know compute stable compute stable solution is easy, right? So we can use the gradient flow, we can use the optimization method, find the stable ones. But we need to compute this unstable saddle point. Okay, it is a tough one. Okay, so to this end, we proposed this saddle dynamics. Okay, so we transform the we try to we calculate the steady solution of this index k saddle dynamics, it will converge to the unstable index k saddle points. Okay, this x is the index k saddles, and vi I from 1 to k is the k unstable directions. Okay, so you just solve this equation, you will the steady state is the index k saddle point, and it's k unstable directions. Okay. And here we use another picture to describe what the difference between saddle dynamics and gradient dynamics. Gradient dynamics, you think you can think it is just like take the slide. Okay. So you have an initial condition, you follow the gradient flow, you will converge to a local minimum. Okay. However, you cannot stop in the middle. Okay. So, but the saddle dynamics is just like you take the stairs. Okay. So you assume you starting from the highest index saddle point. Okay, and you take the stairs. This stair corresponding to its unstable directions. Okay, and you go to next level. Okay, you find it's connected low index saddles. Okay, assume this is the index k minus 1 saddles, and you follow its unstable directions. You can find next level, right? So assume we are in a new building. Okay, so if you take the elevator, you know only one exit, right? So if you want to get familiar with new building, the best way I can suggest is you try to take all the stairs, right? The stairs connect all exit, right? Okay, here this slide shows some numerical analysis of this saddle dynamics. Okay, it's just tell us, okay, you just saw this saddle dynamics. Okay, this solution, this solution is a linear stable steady state of this is the index k saddles and its unstable eigenfunctions, and we can discretize like the Euler scheme. Okay, we have the error estimate, convergence rate, so we can guarantee you got a reasonable solution. Okay. Okay, with this saddle dynamics, we can combine it with the downward and upward search to construct the solution landscape. Okay. As I mentioned, if we're starting from a k saddle, if you do the gradient flow, you will converge a local minimum, right? So, but you will miss the other solutions. Now we don't do that. Okay, we just use the saddle dynamics. Okay, we take the stairs one step by one step. Okay, so here we follow its unstable direction. We use k minus 1 saddle dynamics. We try to find all collected k minus 1 saddles. Okay. Once we find this k minus 1 saddles, we start with each k minus 1 saddle. You use k minus 2 saddle dynamics. They keep going down. Okay, find k minus 1, k minus 2 saddles, k minus 3 saddles. Okay, so so on and so forth. Once we find this one saddles, we just use the gradient flow. Okay, if we use the gradient flow, we can find all possible local minima. Okay, okay. So that's the downward search. Okay, but if you don't know the k saddle, okay, you can start with a local minimum, or you can start with any initial guess. You do the upward search. Okay, you follow this purple line. Okay, starting from local minimum, you do the index 1 saddle dynamics. You find this one saddle, and you keep climb up the stairs. Okay, you find the high index saddles, okay, until you find the highest one. Then you do the downward. You find the other solutions. Okay, just like you find your family tree. Okay, you first need to know your father, then grandfather, right? Keep going down, find the first generation on your family tree, then search, do the downward search. Okay, okay, so that's the numerical method to construct this solution landscape. Here is just a brief remark for the solution landscape. Okay, we believe it proposed it is a new framework for solving the nonlinear problems. Okay. First, this solution landscape reduces the dimension of the problem. Okay. So usually we deal with the high-dimensional example, like the dimension is n. However, the highest index of saddle point usually is low. Okay, this k. Okay, this k index k is much less than the n. Okay, and because it has only k unstable directions, you can just search along this k unstable directions, and the other directions are all stable. So you just reduce the dimension of the problem. And also here we use this high index saddle point as the initial state, and its unstable directions as the searching direction. So we overcome the difficulties of the tuning the initial guess. Okay. Another good property is we are not only find the solution set. Okay, we find the connections between those different solutions. Okay, those two solutions are close to each other. Okay, because they are connected by this single transition state. This solution, with that solution, it has to they are far. Okay, they connected with a couple of index one saddle point, or they are connected to its high index saddles. Okay. Okay. So here, as I just saw the examples for the this energy function. Okay, so here the typical saddle dynamics. It works for the gradient systems. Okay, it can be generalized to the other complex systems. For example, for the non-gradient dynamical systems, okay, we proposed this generalized saddle dynamics. In that case, we don't have Hessian matrix, but we have the Jacobian matrix. So still, we can construct the solution landscape of these dynamical systems. And also, we can construct this constrained systems. Okay, so we can, if we have some constrained manifold, okay, we build up the solution landscape on this constrained manifold. Okay, we have the constrained saddle dynamics. And also, sometimes we don't know exact model, okay, of this system. We propose the data-driven saddle dynamics to deal with the model-free system. Okay, and here is some applications of the solution landscape. For example, the liquid crystals, quartz crystals, and cell fate, protein folding, deep neural network. Okay, and in the remaining talk, I will introduce some applications. Okay, so the first application is the defect landscape of liquid crystal. Okay, so we know that these liquid crystals have the properties between solid and liquid. Okay, so solid, the crystal, it means it has a long-range ordering of its mass center, and also has the long-range ordering of its orientation. But liquid crystals usually do not have the long-range ordering of the mass center, but it has the long-range ordering of its orientation. For example, like this nematic liquid crystal. Okay, so its orientation has the long-range ordering. Okay, and we know this liquid crystal has a huge value in industry. Okay, like this our LCD monitor. Okay, all built off this liquid crystals. So there are many mathematical models of liquid crystal, okay, and also attract many mathematicians to study the liquid crystal. For example, Zhang, Fanghua Lin. Okay, so they all studied this mathematical models of liquid crystal. And here, from the detailed ANSAG molecular model to the Landau Digens tensor model, or to the X-Leslie vector model. Okay, there are many of them. And 2 years ago, with Professor Pingwen Zhang and Wei Wang, we wrote a review paper for the modeling and the computation of liquid crystals. Okay, so you can read it for the liquid crystal. Here I just show you one example. We use this Landau Digens model. Okay, here this Landau Digens model is a phenomenological theory to describe the liquid crystal. Okay. It uses 3x3 symmetric twistless tensor as the order parameter. Okay, and describe the orientation of the liquid crystals. And here is the energy functional of the Landau Digens model. Okay. Here we use tangent dirichlet boundary conditions so that the liquid crystal align along the boundary. Okay. So here the blue color means the position of the defects. Okay, so the four corner had 4 defects, and there are 2 typical defects you can see. One is the diagonal. Okay, the liquid crystal align along the diagonal directions, and the other one is rotated. So the liquid crystal rotate to its neighbor corner. Okay. So although there are some numerical methods to compute different defect configurations of the nematic liquid crystal, but so far nobody people don't know how many possible configurations of this nematic liquid crystal. And here we will apply our solution landscape, construct the complete defect landscape of this nematic liquid crystal. And here totally we found 89 defects, and that's the complete solution landscape. Okay, and include some new defects. Okay, they have not been reported in the previous literatures. And also we found interesting this dynamical pathways. It describes from the highest saddle point, okay, to the stable defects D. Okay, that's the follow the saddle dynamics. Okay. And here you can see that how these defects, the evolution of the defects make the defect patterns more and more stable. Okay. And if you don't know the highest index saddles, okay, you can using the upward search from a local minimum D, follow this this blue dashed line. Okay, goes up. Okay, here from M to N. Okay, you can follow the saddle dynamics. Okay, from N plus, and eventually they can climb up the highest the WS. Okay, the most unstable solution. Okay. So we are not only compute the solution landscape, we can also plot this bifurcation diagram to show you the evolution of the solution landscape. And here you can see that this alpha is a critical parameter, describe the square size. If the alpha is small, there is only global local minimizer, is global minimizer WS. It looks like that. If we increase this parameter, okay, this solution becomes unstable. Okay, it will bifurcate. Okay, it becomes the first become the index 1 saddle, then index 2 saddle, and the index 4 saddle till the index 6 saddle when alpha is equal to 650. Okay, here we just compute alpha is equal to 50 this case. Okay, and along this when this parameter increases, you see there appears many bifurcation. There appear many bifurcation process. Okay, so this larger domain means it can contain more defects. So we have more complex solution landscapes. Okay. So this is the example for the square domain, and we can extend our work to study the effect of geometric domain on the numbers, locations, and its dimensions. Okay. For example, we can compute on the solution landscape on the hexagon. Okay. Also, we extend our calculation from 2D to the 3D. Okay, here we construct 3D non-homogeneous solution landscape. Okay, find many interesting results here. Okay, I omit those details. Okay, solution landscape can also serve as an efficient tool for the model comparison, okay, which means to describe the defects, you can use non-homogeneous model as I talked in the previous slides, or you can use the action-Leslie vector model. Okay. But what's the difference between those two models? Okay, here we compute the both solution landscapes, both action-Leslie and the non-homogeneous model, and compare what's the difference. And if you only look at those local mini-measures, okay, they are very similar to each other. Okay, they also have this diagonal solutions. But if you look at the whole solution landscape in the action-Leslie model, okay, we found many those this kind of solutions. Okay, they have this line defects. We call the non-physical solutions, but they do exist in this action-Leslie model because this action-Leslie vector model lack of the head to tail symmetry, which means the vector rotates 180 degrees, it becomes to another one. Okay, so which means this this vector model, okay, can produce some fixed solutions in this case. Okay, that's the first example. And here is the second example. We studied the nucleation quasicrystals. Okay, so why we interested in this problem? Because for the previous one, okay, for this solution landscape of this liquid crystal, okay, there are already some numerical methods to construct these defects. Okay, although it's not complete, but they do find some different defects configurations. Okay, and over here we want to show you one example. The other method cannot do it. Only our method can do it. Okay, so that's why we consider this nucleation of quasicrystal. And so here we know this crystalline structure has the periodic and the symmetry properties. Okay, like the crystal can have both 2, 3, 4, 6-fold symmetries. Okay, like this table shot. Okay, and for the periodic structure, okay, it has translational symmetry. Okay, like if you do the tiling. Okay, if we want furnish our house. Okay, in the kitchen or the bathroom, you just do the tiling. Okay, so here one interesting mathematical problem is this tiling problem, covering the plane without gaps and overlaps. Okay. And we can prove that if you use this equal polygons, okay, do the periodic tiling, okay, you can only use the triangle, square, and the hexagon. Okay. If you use the pentagon, it has some gaps or overlaps. And this Roger Penrose, he won the Nobel Prize in 2020. Okay, he proposed interesting Penrose tiling. Okay, it's an aperiodic tiling, which means no invariant by translation. Okay, they use 2 different diamonds to the tiling. Okay, so in the middle they use the 5 blue ones and surrounded by the 5 green diamonds, and keep doing that. Okay, eventually they can cover the plane. Okay, and if you look carefully, you see this pattern has no invariant by translation. Okay, you cannot translate on the plane. Okay, and also there are some examples of this aperiodic tiling. Okay, but this kind of pattern, okay, people are wondering, is it just a mathematical game? Okay, so in reality, we cannot find this aperiodic pattern. Okay, all so people usually believe that in nature all structures are periodic structure. Okay, so this question is answered finally answered by this Dan Shechtman. Okay, he discovered this quasicrystal. Okay, in 1984. Okay, for the discovery of the quasicrystals. Okay, in nature. Okay, and then won the Nobel Prize in 2011. Okay. So this quasicrystals just means the quasi-periodic crystals. Okay, so they found this aperiodic structure. So although people already found many quasicrystals in world, but here the question is the emergence of the quasicrystalline order from crystalline order. Okay, this is a long-standing unsolved problem. Okay, what's the meaning for that? So we know the liquid and the crystal, they can convert to each other by the liquid. You do the cooling. Okay, you can got a you got a crystal, and crystal you increase the temperature, you got a liquid, right? So quasicrystal is obtained by the rapid cooling from the liquid, so that you can get this aperiodic structure. However, the crystal between crystal and the quasicrystal, can we obtain the quasicrystal from crystal by some nucleation event? Okay, this is the question. Okay, people don't know from the experiments or for the theory, people don't know the answer. Okay, so here why this problem is very hard, because here we saw this example. Okay, this C6 is the 6-fold crystals, and this QC is the 12-fold quasicrystals. And you can see that there are no obvious epitaxial relations between those crystals and the quasicrystals. Okay, so that's the in the physical space, and here is the reciprocal space. Okay, so you can see this their spectra are also very different. Okay, so it means it's very hard to imagine if you cut off part of the C6 and put QC inside of this C6. Okay, how their boundary, okay, how their interface match each other, right? So this one is very hard to imagine. Okay. So here we use the phase field crystal model to study the nucleation from crystal to the quasicrystal, and I omit those details here. In particular, we apply this Lipschitz-Petrich model. Okay, they use two length scales. Okay, this one Laplace plus one. This describe the make the C6 as a steady state, and this Q, if Q is chosen by 2 cosine pi over 12. Okay, it makes the 12-fold quasicrystal stable. Okay, so here so that we can make the C6 and the QC coexist in the phase diagram. Okay. And here we compute this phase diagram of these quasicrystals. And here we only have two parameters, epsilon and alpha. Okay. So here we tune those alpha and epsilon. We got its phase diagram. C6 is the crystals. QC is the 12-fold quasicrystals. And interestingly, we found between C6 and QC there exists a certain area. There we found a new phase. It's called LQ, lamella quasicrystals. Okay. This one, if you look carefully, okay, along y direction, it is a periodic pattern. Okay, but along the x direction, it's quasi-periodic. Okay, so that's what we call the lamella quasicrystals. Okay, so this phase is quite important during in the nucleation. Okay, and computing the critical nucleus for the quasicrystal is a very challenging problem, because first this LP model is an 8-order system, so it's it's EO-Posnius. Okay, so and also this degeneracy of C6 and QC. Okay, which means C6 has 2 zero eigenvalues and QC has 4 zero eigenvalues. Okay, so it causes degeneracy. And here we apply this our saddle dynamics. Okay, we shoot for the high index saddle point in order to find this index 1 saddle point, okay, to overcome this degeneracy. Okay, so here the case 1 is from liquid to quasicrystal. We studied this process, this nucleation process to validate our model. Okay, so H is the homogeneous state corresponding to the liquid, and in the middle you see this nucleus appears. That's the critical nucleus, and eventually it occupy the whole domain, becomes the quasicrystal. So here you see the critical nucleus appeared in the middle. Okay. So that example just to validate our model can study the nucleation event. Then we try to study this from the crystal to the quasicrystal. Okay. So in this case, actually, we identified 2 transition pathways connecting crystal to quasicrystal. One is the one-state directed pathway. Okay, so it's the from C6 we do find it's a nucleus of quasicrystal and eventually go to the QC. But its energy barrier is high, and another path we find a 2-stage indirect pathway. First, C6 along there's a nucleation event. It becomes to the LQ phase, and this LQ overcomes another energy barrier, becomes the QC phase. Okay, so this 2-stage pathways has low energy barriers, which means it's more probable. Okay. So this paper was published in 2021, December 2021 in PNAS, and in January 2022, the Science journal, okay, they has editor the session in other journals. The editor recommended our paper. Okay, comment that despite decades of active research on quasicrystal and their discovery in nature, but the mechanism of quasicrystal nucleation remains unclear. And we obtained an interesting picture of critical nucleus and the minimum energy path. Okay, that could shed light on how quasicrystals emerge from the crystalline phase. Okay. It also points out our proposed methodology is general and applicable to other physical systems undergoing the first-order phase transitions. Okay. Okay. So in the last few minutes, I saw another example. We studied the excited states of the Bose-Einstein condensate. Okay. Thanks for it's very related to Professor Bose talk. Okay. So he already introduced, gave a very nice talk to introduce this background of the Bose-Einstein condensate. Okay. So here we know this quantum gas. Okay. If we decrease the temperature to the near 0 Kelvin, okay, those all particle shows the occupy the same wave state. Okay, so we call it is a BEC. Okay, so this BEC, after Bose and Einstein proposed the existence of the BEC. Okay, those 3 scientists, Cornell, Kettler, and Wieman, they validate. They found this BEC phenomenon in experiments and won the Nobel Prize in physics. Okay, so here they found this BEC condensates as the 5th state of the matter. Okay, and describe this. They have caused the atom to syn in unison, which means all particles on the same state. They syn together. Okay. And here the ground state, okay, the ground state, which means the stationary state with the lowest energy. When we're talking about excitation, which means the energy is higher than the ground state. Okay, so those excited states, which means we absorb energy to transition to the high energy state. Those excited states may corresponding to the local minimizers or the saddle points. Okay. So although there are already many computational efforts for finding the ground state, the global minimizer, okay, but the excited states and the excitation mechanism between different vortex states remain a mystery. Okay, this means how the ground state they can excited to the first excited state and to the second excited state to the next one. Okay, so that's the question we are trying to answer. Okay, again, so we can again apply our solution landscape to study this Gauss-Pitavisky equation. Okay, here Professor Bose already introduced the properties of this GP equation, so I'll omit those details. Okay, so basically we just calculate the GP energy. Okay, and try to solve this Euler-Lagrange equation. Here, because in this system it's a constrained, we have the mass conservation, so we use the constrained high index saddle dynamics. Okay, so here we replace gradient by the Riemann gradient and replace Hessian by the Riemann Hessian in order to satisfy these constrained properties. Okay, and here is the evolution of the ground state and the stabilization process. Okay. Here, omega is the rotation frequency. If we increase the rotation frequency omega, more vortex will appear. Okay, and we did further investigation, found that those vortex state actually at the beginning they appear as the excited state and become ground state, and again become change to the excited state again. Okay. So for example, this P2. So when omega is equal to 0, they are not appear. Okay. So they appear by this saddle node bifurcation. Okay. So P2 and the SP2, they are very close to each other. Okay. So one is the index 1 saddle, and SP2 is the index 2 saddle. Okay. After a pitchfork bifurcation, P2 becomes stable. Okay. And but in this place, it's a local minimum, and eventually it becomes a global minimum, and after then a local minimum, and they merge with P2SP by another pitchfork bifurcation. This one and that one, they become the index 4 saddles. Okay. So that's the bifurcation process for P2, and for the other like P3, P4, they following the similar bifurcation diagram. So that's the evolution of the ground state. For the excitation, here we use the constrained high index saddle dynamics served as the inverse gradient flow corresponding to the excitation. Okay. So which means C, the increase energy becomes B1, and they keep increase energy become another excited states. Okay. And here we identify a couple of excitation mechanism. Okay, first one is the vortex addition, which means we increase a new vortex from the far field. Okay, so following this line. Okay, so we keep increasing, we can get high and high excited states. Another is vortex rearrangement, which means the number of vortex are not changed, but they just remove the position of this the vortex. Okay, so they can also increase its energy, become to the high excited state. And another excitation mechanism is vortex merging. So it means two small vortex merge to one large vortex. And the vertex splitting, it means those 3 vertex split to 5 vertex. It can also become high energy. Okay, and here we compute at omega is equal to 0.45. We compute the spectrum of the BEC stationary state. This is the ground state. This one first excited state, second one, and here we compute. This is so far the most complete spectrum of BEC stationary states. Okay. Here is not complete because for the after this P4, actually there exist many other high excited states. Okay. So here again for the ground state, we can you can think it's a global minimizer, so it's seen in the unison. And here we discovered the excited states of the BEC, which means we can increase its energy, make this vertex to dance. Okay, so we describe it as the dance together. Okay, here is the summary. So we introduce a solution landscape, which is a pathway map from a parent state to all minimizers. Here we use the saddle dynamics to construct a solution landscape, find all possible solutions. And we give 3 examples: nematic liquid crystal, nucleation of quasicrystals, and excited states of the BECs. And we believe this solution landscape is generic and can be applied for a wide range of nonlinear PD problems, non-convex optimization problems, and many applications in other science. Okay, and that's my collaborators and my group members. Okay, that's all. Thank you very much.
Any questions?
So I'm wondering how efficient is this saddle dynamics method? So for instance, for a nonlinear problem, you design a gradient descent method to find a local minimum. So how the computational time compared to the gradient descent method to find the minimum?
Let me go back to the saddle dynamics. That's a very good question. So here, you can think about our saddle dynamics is a modified gradient flow. If there is a V is equal to 0, it means no second equation, only the first equation. It is just a gradient flow. Okay, and here the additional effort we need to calculate is the eigenvalues, eigenvalue and eigenfunctions of this Hessian matrix. So if you want to calculate the index 1 saddles, you need to calculate its 1 eigenfunctions. So you have another one equation for V. Okay, then you combine them. So this again is just a modified gradient flow. So actually calculate the eigenvalues. You have many efficient ways to calculate. You can use log PCG method. You can use the other efficient numerical method. So as long as you can quickly calculate local minimum by the gradient flow, actually you can quickly calculate this saddle points by using the saddle dynamics.
Other questions?
Yes.
Okay. I realize in your notation for example, Bose Einstein, Einstein, you write E of phi. Phi is a function.
That's right, functional.
So and then this phi is same as this isonorm.
This gradient E, it could be the energy function. Also, it can be energy functional. So
functional.
That's right. Yes. It's just like you do the energy variation. Okay. So if you know without this part is a gradient flow for the energy variation, and here we just do the similar things. We just calculate its its eigenvalues, eigenfunctions to convert to get the version of this saddle dynamics version for this energy function. So
then also you about this Hessian. S is infinite many-dimensional. This also involves this this Hessian of E, right?
Yeah. This was similar. This is also similar. So for the energy functional, we do the same thing. You just here we use the tilde, which means we don't need to calculate the exact Hessian. We just do the finite difference. So again, we only need to do first derivative of this energy functional. Yeah, so it's similar.
Okay. Another question is, do you have a general algorithm for when you have the degeneracy saddle point?
Degenerate.
Degenerate, because you all assume your saddle points are non-degenerate.
Yeah.
I realize you have some examples where you treated the degenerate one.
That's right. Yeah. At the beginning, when we introduce this concept, non-degenerate make it much simpler. In practice, we can deal with both non-degenerate and the degenerate case. For example, the second example, nucleation of the quasicrystals. Here we have the degeneracy because the quasicrystal it has 40 eigenvalues. So in that case, when you do the saddle dynamics, one way we do it is we count this degeneracy, which means you calculate index 1 saddle point, okay, and with 40 eigenvalues, you need to use the index 5 saddle dynamics. So this index 5 saddle dynamics, it will convert to the index 1 saddles with 40 eigenvalues. So in that case, we can overcome the degeneracy caused by the pollen.
Okay.
Yeah.
Last question.
So
maybe the last question is a pedagogic one. I mean, if I give you a quadratic form, infinite dimensional, for example, quadratic form, right? And then with the matrix A, and A has some negative eigenvalues and positive eigenvalues, but no zero eigenvalues.
Yes.
And can you do that, right?
Yeah. Yes.
And then what can you? I mean, my question is, and then can you with this function you can explain the algorithm probably more clearly?
If here the actually here the difficulty we use the saddle dynamics. Here the unstable direction and the stable direction is not you cannot determine as prior information because as we can only find its unstable direction when you when it converts to the solution. If it's a min-max problem, it already separate. Actually, that problem is much simpler than the problem we consider here, because you already have the separate structure. So you can use min-max optimization algorithm to solve it. So here we need to find this unstable manifold first, then to calculate the saddles. Maybe we can discuss later too. Yeah. Okay.
Any other questions? So let's thank the speaker again. And we have another